My engineering technology 415 project. It's based on hydroelectric power. That was my uh, topic of choice. The research article or research paper that I reviewed or looked over and summarized and I'm going to be presenting today is titled An Approach of the Hydropower Advantages and Impacts, a Review. It's by Sebastian Naranjo Silva y Javier Alvarez del Castillo. The abstract of the paper. Within the abstract, it states the purpose is it does an overview of the advantages and impacts of hydroelectricity. It does so by, um, well, their method is that they set a specific criteria and keywords as parameters when searching specific websites for articles and theses and whatnot. They were looking for specifically impacts and benefits of using hydroelectricity and building the infrastructure for that, whatnot. The conclusion within the abstract concludes the paper concludes that hydroelectricity is a viable renewable energy source, but it has impacts on the environment and the ecosystem that must be considered, such as just how will obstructing the flow of water affect the ecosystem downstream versus upstream, whatnot, all that. Introduction: the importance of this study. About three-quarters of the greenhouse gas emissions come from electricity and heat transport, which is the energy sector. Um, yeah, it's mostly supplied by fossil fuels. That's the main means of generating electricity and energy and heat. Some background on hydroelectricity and hydropower in general is about well, in the 70s, 80s, hydroelectricity generated about 26% of the world's energy. And then I think it peaked in percentage wise, I believe the paper said. Um, and then hydro grew from 200 billion kilowatt hours in 1946 to 860 billion kilowatt hours in 1965, and then to 975 billion kilowatt hours in 1978. So it's been kind of a steady increase, although as you can see from the 13 years between 65 to 78, it was kind of a smaller increase than the about 20 years from 46 to 65. So it kind of grew and then it kind of is balancing out a little or topping out. There's around 1,300 gigawatts of total hydropower capacity. Uh, Now as to regions and their consumption of energy from hydropower, the Asian Pacific regions primarily use power generated by hydro. It's due to just their abundant access to water, rivers, and whatnot, ocean and stuff. And it's just been increasing since it's an easy source they can set up since they have an abundance of water. Uh, Europe, North America, and kind of those regions, they've kind of maintained a stable amount of usage of hydropower. It's not been increasing or decreasing. It's just kind of been steadily growing with energy demand and whatnot. Just because they don't necessarily have as much access to that, but they also have access to other forms of power and electricity. Um, Regions like the Middle East and Africa use the least amount of power from hydro. It's because hydropower uses water, and water in those regions tend to be more scarce and sought after, and they don't have as much of abundance of it to effectively uh, harness and use it, especially with trying to use it and getting into political stuff of like, river flows from one country into another, and then you use it upstream, it affects downstream, and then more political conflict, whatnot. Um, that's why it's pretty low in Middle East Africa. Nowadays, 4,000 billion kilowatt hours of power is produced by hydroelectricity. Let's move on to the figures. These are all taken out of the, um, what we call it, the paper. So figure one is just a global greenhouse gas emission by sector. It kind of just breaks down where the most percentage of greenhouse gas emissions are coming from, and as you can see, about three-quarters is from the energy sector. The other quarter is from waste, industrial, agricultural. So it's kind of important to get up renewable energies and whatnot to significantly reduce the ener or the greenhouse gases emitted from the energy sector. Figure two just shows the world renewable generation. So it kind of just breaks down the terawatt hours produced by year based on whichever renewable energy we're looking at. As you can see, hydropower is just the most mature and the most widely produced. It's just, well, just in general, hydropower has been around for a while. Even back then when they have like water mills and whatnot to use a little bit of river power to spin stuff. So it makes sense that it's been the most mature since it's been the most used, while wind and solar have been growing in usage due to, well, more advancements in technology to make it more viable and whatnot. Figure three shows modern renewable energy generation by source. Um, it's the same as the site or the figure two, just instead of stacking them on top of each other, it just gives you a line to kind of show you what it actually looks like amount wise rather than just seeing things stacked on top of each other as a total summation. Yeah, you can still see the hydro is what, a little over like almost triple that of wind. Um, yeah. And then figure four shows hydroelectric capacity installed in the world. It kind of just breaks down where the capacities are located and whatnot based on country. As you can see, China, US, Brazil, those big players are kind of all have a large amount. And then figure five is hydroelectricity consumption by region in exajoules. Um, yeah, I learned about exajoules through this. It's well, exa is just the prefix. It's 10 to the 18th. So it's like what, one exajoule is 1 quintillion joules. So it's a large amount. It's 10 to the 18th. Um, so you can see that by year it can show you the amount of joules produced. And then you can see by region. It's it's a lot of energy. Okay, so the methods and methodology used, methods used, they consolidated concepts through bibliographic review of scientific articles published from January 2013 to May 2021. Specific website used are Science Direct, Taylor and Francis, and Springer. Specific search parameters are selected to find relevant articles. Use keywords like hydroelectric forecast, advantages and disadvantages of hydropower, and pros and cons of hydroelectric development. That's just how they found the articles, and then they went through them and cited them and used them as sources for their paper. The results and discussion: hydroelectricity is the primary renewable energy in global deployment. It's just because it's the most mature. It's just big infrastructure already. Uh, there's going to be a decrease. Multiple studies show that there's a projected decrease in the usable power capacity of hydroelectricity just due to climate change and, well, yeah, climate change and just kind of reducing the available amount of water. Advantages. Let's see. Facilities act as a means. Oh yeah, this is the advantages. It's from table. I think it's the only table in the paper. It's table one. Um, it basically gives breakdown of advantages and disadvantages. I have the advantages summarized here, and then later I'll have disadvantages following. So, advantages: the facilities, like the dams and whatnot, that harness it can be used as a means of flood control due to just that it can hold water. So then, if there's excess water that would cause a flood, it would just build up in the reservoir instead. So it allows control of a flood. Um, Pretty neat. Hydroelectricity has lower greenhouse gas emissions compared to fossil fuels. It's significant lower. It's estimated that 4 to 14 grams of CO2 per kilowatt hour for a greenhouse gas cycle for hydropower. Um, Storage reservoir acts as a means of consistent water flow to combat droughts. Yeah, so the water buildup there and just the kind of storage of there, they can combat droughts as well. So if there's like less water flow, they have a reservoir that they can keep a steady stream going, so it doesn't just like dry up or significantly reduce the amount of water in the river. Um, it's pretty competitive price-wise per kilowatt hour. The weighted average for cost of new hydropower projects is around 5 cents USD to kilowatt hour, which is pretty low, and it's comparable to that of thermal energy sources such as fossil fuels. Um, the hydroelectric power provides jobs and opportunities to people since they're big projects, so it can attract work and just maintaining it as well and working it, so you can kind of have a stable job for that. Hydroelectric power has a pretty high efficiency of 55 to 92%. Um, it's kind of easy to harness a lot of the kinetic energy from water with the amount of time we've had to learn and experiment with building things and turbines and whatnot to do so. Um, they have a pretty low maintenance cost to be sustained. The number of workers that are needed to run a hydro plant is a low ratio of 0.25 people per 1 megawatt of energy, compared to that of like say nuclear and or thermal power plants. Nuclear is 1.05 people per megawatt, and then thermal is 1.26 people per megawatt. So it's a good ratio. It's pretty low maintenance once it's been built and done. It can drive investment in smaller communities where it's being built as it brings work and then just corporations and whatnot to build that and supply the stuff there. So then it kind of builds up the surrounding place. The disadvantages: the facility separates rivers and changes the ecosystem, so the upstream and downstream will be separated, and that can change the aquatic ecosystems along with downstream ecosystems and upstream due to excess water and lack of water. Um, and then power generation changes a little bit, so the more power that's needed, the more water that'll flow through usually, which then causes irregular amounts of flows downstream, which can cause different or cause erosion rather than if it's just a constant stream. There are greenhouse gases in hydroelectric dams because of the reduced oxygen concentration in the water. The upfront cost of building a dam and laying the lines requires a high budget. It's a pretty big investment, but the amount of money you pay per power is pretty competitive still. It accelerates the destruction of an ecosystem since it's often located in tropical regions, which have ecosystems that rapidly decay and kind of go through processes faster. So then when you change variables like that, it'll show up significantly faster in those tropical regions than, say, a more temperate region. To maintain high efficiency, the dams are usually in test conditions like low seasonality, so low variations in the amount of water, flow rate, whatnot. So if there's variations, it could make the efficiency vary. Hydro plants are investment. They take like 10 to 20 years to build, so they're not the most easiest resource to get online. Conclusion. Findings of the work. Overall, hydropower brings many benefits, such as water supply to a community, flood control, and low greenhouse gas emissions, although there are downsides that must be considered before undergoing the installation of infrastructure, such as changes in the local ecosystem and changes in water quality. Hydropower is an investment that should be paired with other renewable energy sources to work towards minimum greenhouse gas production in the energy sector. That about summarizes the paper. On to part two of my project. I chose to investigate Francis turbine. So the introduction, brief overview of it is Francis turbine is a type of reaction turbine that is used in hydroelectric power production. The turbines use both the reaction force, so that's like the kinetic energy from the water, and then also impulse force, which is also from the head due to the pressure of the water. It's the most used turbine in hydropower. It's been around for a while as well, so it's been optimized and whatnot, so it's pretty efficient since it uses both uh, reaction and uh, impulse, and it has a wide range of levels of flow and head that it can work in. Motivation. Why is it important? It's the most widely used turbine in production, so I decided to look a little more into it just because it's pretty big. Why am I interested? Um, I mean, I kind of just in general enjoyed fluid dynamics, and I chose something pertaining to fluids, and then going into a turbine, and it's basically just a pump. Uh, pretty interesting. I just kind of want to understand how it works. So technical details. Working principles. A Francis turbine consists of the following components: a spiral casing, guide vanes, stationary vanes, draft tube, runner blades, penstock, and a runner. You can see in figure 1 that it is a cutaway diagram showing the Francis turbine. You can notice the large diameter on the right, and then as it decreases in diameter on the left. I'll talk about that a little later. Okay, getting into the components. The spiral casing acts as an inlet and guides the water towards the turbine blades. The guide vanes direct the angle of attack that water has when entering the turbine. So yeah, the spiral casing specifically is the one that has decreasing um, diameter. It's due to when you bring water through and you turn it into kind of rotate it like that, it takes some energy out of the system, therefore decreasing the pressure. So then the decreasing diameter shoots the pressure back up and makes the water maintain its pressure to account for the energy loss of trying to turn the water from going linear into more of a centrifugal uh, movement. Um, Stationary vanes reduce vortexes in the water, so it kind of just makes it less turbulent. So when the water hits the runner blades, it doesn't. It's not turbulent, and it hits it more straight on in a more laminar manner. The draft tube is the drainage. It's the exit below the runner. That's where the water drips out after it's been used and spent. The runner blades are the blades that take the kinetic energy from the water and turn it into mechanical energy to spin a shaft. There's two parts of the runner. The upper blade is the reactionary part. It catches the kinetic energy, while the lower part is more bucket shaped like a Pelton turbine, so that it can use impulse force by taking like impulses of the water. So it's good for if there's high head and low flow rate, that it can still maintain high efficiency, versus if it was high flow rate, low head, then the top part of the blade would generate more power. The penstocks, the pipe that takes the water from the reservoir and transports it to the turbine. The runner is the hub that that's connected to the runner blades and the shaft that spins. Yeah. Francis turbine can achieve anywhere from 90 to 95% efficiency. The turbine also has a range of power generation from a few kilowatts to up to 1,000 megawatts. Considerations: a big issue with dealing with fluids in general, especially water, and going from high pressure to low pressure suddenly, is cavitation. Basically, it's when you have water at a specific temperature going through and it drops in pressure, and the pressure drops below that of its saturated vapor pressure, I believe. Uh, Probably should have looked that up real quick, but it basically drops below that pressure and it turns into a vapor at that point because it's at that temperature and pressure where it can be a vapor. You just have to consult the table, look and see what that would be, which then causes vapor air bubbles to then go up back through the system, meet with the area of high pressure, and explode, which can damage the runner and the runner blades and overall just destroy the turbine. So it's a big concern that you have to consider. Applications: it's used in hydropower due to its versatility, and it's about a medium head range. So it can be applied in a range of 130 feet to 2,000 feet. So it's about 60 meters to, what is that, 600 meters? The turbines can also be used in irrigation to transport water from the ground to surface. You could basically hook it up to a generator, put in water, and then change it from a turbine that intakes water to a pump that then intakes water and then pumps it out. You just reverse it. Instead of it taking energy from water, it puts energy into the water. Cost analysis. I looked up online. I found this equation through a website that basically gives a cost breakdown of what was a UK website, so it gives pounds sterling's 2008. So I just put together a theoretical little example because I don't really have like a set parameter, so I'm just like kind of picking one so that you can get an idea of what it would cost at these specific parameters. So for a turbine that has 100 meters of head and a flow rate of 5.4 meter cubed per second, With those parameters, you plug it into the equation below, you can get $587,896.10 for that turbine based on those parameters of what it needs to fill to build it. Conclusion: overall, the Francis turbine is a commonly used turbine used in hydropower generation because of its high efficiency and adaptability. It sits at the mid-range of head levels, so it can be used in most plants when compared to a Kaplan turbine, which is good for low heads, and Pelton turbine, which is good for high head values. Yeah, there's my references. Neat.